In this video, we're going to discuss the limitations of FriedelCrafts reactions. Our first limitation is that FriedelCrafts alkylations use a carbocation as the electrophile. And as we know from previous chapters, anytime you have a carbocation, a rearrangement is possible. This means that if we want to add on a single unbranched chain to a benzene ring, we're not going to be able to do this through FriedelCrafts alkylation in a primary alkyl halide. For example, look at the reaction below. In the first step of this reaction, we would form the electrophile. This occurs when the bromine interacts with the aluminum chloride in a Lewis acid-Lewis base interaction. This is going to form a complex ion. In this intermediate, we have a negative charge on a metal, which is never really a very great idea, and we have a positive charge on bromine, and we know that bromine is electronegative, so it's probably not very happy with this arrangement. So this is not a particularly stable complex, so what's going to happen is bromine is going to leave and take those electrons from the covalent bond with it. This will give us our carbocation intermediate. However, our primary alkyl halide yields a primary carbocation. And hopefully we recall from previous chapters that a primary carbocation is actually pretty difficult to form because it's not very stable. So what happens next is a hydride shift in order to create a more stable carbocation. It is this secondary carbocation that we've created that's going to be our electrophile. So when benzene goes to attack the electrophile, we're not going to get an unbranched chain coming off of the benzene ring, as you might have thought by looking at the starting reagents. Once we're at this intermediate, our next step is to deprotonate and reform our aromaticity. We will actually use the bromide ion from our complex ion to accomplish this, which will give us an equivalent of HBr as part of our product. We also end up with an equivalent of aluminum chloride, which shows us that aluminum chloride really is a true catalyst in this reaction because it appears in the beginning, it gets used in the reaction, and then appears again in the product. So we are not actually using up any equivalents of aluminum chloride. Our next limitation is that FriedelCrafts reactions are deactivated by the presence of an electron withdrawing group on the benzene ring. The benzene ring needs to be electron rich in order to initiate the reaction between the pi electrons and the carbocation intermediate. The following groups are electron withdrawing: your nitro group, a halogen substituted carbon, sulfonic acid, a quaternary ammonium, carboxylic acid, ketone, any carbonyl compound. So you could throw in an ester or an amide or an aldehyde. As long as the carbonyl carbon is directly attached to the benzene, it's going to be a deactivating group. Also, amine groups are deactivating in a FriedelCrafts reaction, even though an amine group, not an ammonium, an amine group that still has a lone pair, an amine group is an ortho-para director and is typically an activating group for most reactions. But in a FriedelCrafts reaction, we have the added complication that the amine group is going to associate with the aluminum chloride, forming a complex ion with a positive charge on the nitrogen. This is going to make this a deactivating group. When we get to the portion of the chapter that discusses directing groups, we'll talk about why certain groups are deactivating or activating to benzene rings. This particular slide is referencing deactivation in terms of FriedelCrafts reactions only. Our next limitation is that aryl and vinylic halides do not make carbocations readily, which means they cannot form our necessary electrophile readily. And if you cannot create the electrophile easily, then you're not going to be able to get a FriedelCrafts reaction to occur. And that's going to mean that this reaction is a no reaction. Our next limitation is that polyalkylations often occur. The issue being that alkyl groups are electron donating, which means that they enrich the benzene electron density and make the benzene ring more reactive. So you add on one alkyl group and any remaining alkyl starting material is going to continue to react with the benzene ring. So for example, in the reaction below, even though this is not specifically a Friedel-Crafts reaction exactly, we have benzene, isopropanol, and boron trifluoride. You're going to definitely get the addition of one isopropyl group, but you're also going to end up with two isopropyl groups, and you're going to end up with a mix of products because this product is more activated than the original benzene. And so if you have unreacted alcohol, it's going to choose to react with your product over reacting with the other starting material. So you may also end up with some benzene that did not react at all. So if you want to control the alkylation, you can use acylation instead because we do not need to worry about polyacylation. Acyl groups are electron withdrawing, so when you add on an acyl group, you are actually deactivating the ring and you're not going to end up with this polyalkylation issue. So for example, if you react benzene with acetyl chloride in the presence of aluminum chloride, you're going to get acetophenone. But when you try to react acetophenone with acetyl chloride, you're not going to get a reaction because acetophenone is deactivated and therefore will not participate in a Friedel-Crafts reaction. So we're going to do a practice problem. Go ahead and pause and take a moment to attempt this problem on your own. So in the first step of this practice problem, our alcohol reacts with thionyl chloride to give us an alkyl halide. This is a reaction that we're familiar with from OChem 1. Now in the next step, we are given aluminum chloride and benzene. This tells us that we are about to do a Friedel-Crafts reaction using this alkyl halide as part of the starting materials. So what we need to do is determine what our carbocation is going to look like. And in the previous videos, I showed you that you can actually kind of jump ahead a couple steps. You don't really need to draw out the complex ion and then show the dissociation. It's very clear that what's going to happen is eventually this leaves and leaves behind a carbocation. Now this carbocation is primary and it's next door to a quaternary carbon. Is this the best carbocation that we can make in this situation? Hopefully you said no. What we can do instead is move this methyl group over in an alkyl shift and create a better carbocation. This carbocation is tertiary, which is definitely much better than the primary carbocation that we started out with. That means this is the electrophile that benzene is going to attack. Now, once you've drawn your product, this is definitely a situation where students start to lose carbons. So I want to go over just how to compare your product to your intermediate real fast to make sure that you ended up with the correct product. So this is the bond that was formed during the electrophilic aromatic substitution reaction. And in our substituent here, we need to have 1, 2, 3, 4 carbons all in a row, and a methyl group coming off of carbon number 2. So if we look at our product, we have 1, 2, 3, 4, and a 5th carbon coming off of carbon number 2. This tells us that we probably have the correct product. Now the reason drawing out your carbocations is important is that if you didn't do this and analyze your carbocation and recognize that there was a rearrangement, you would end up drawing the completely wrong product. These two products are very different and came from two different approaches. This shows me that you didn't think about the electrophile intermediate and realized that it was going to rearrange to the more stable carbocation. So there has to be a way to get around these alkylation rearrangements so that we can create a benzene with a single unbranched alkyl chain. The trick here is that FriedelCrafts acylations do not undergo rearrangements, so we can actually use them to add exactly the carbon chain that we want to add, and then we can remove the carbonyl. FriedelCrafts acylations do not undergo rearrangements because their intermediate is the acylium ion. And since there is only one carbonyl carbon in this compound, there is only one possible acylium ion, and it's not going to rearrange. So here's our plan. We add on an acyl group with our desired carbon chain, whether that's a single unbranched chain or just, a chain where we have some high degree of substitution somewhere else, but a low degree of substitution at the point of attachment to the benzene ring. And then we reduce the carbonyl. We can remove it using Clemenson or Wolff-Kishner reductions, which are both reactions that we haven't actually learned yet, but we are going to go over the mechanisms and learn them in more detail in Chapter 16. So the Clemenson reduction uses a zinc and mercury amalgam heated in hydrochloric acid. So this is a very safe reaction, obviously. And all it does is completely remove the carbonyl. So in the first structure, you see that you have a ketone. In the second structure, that carbonyl is gone, and the carbon chain will be unchanged. In the Wolff-Kishner reduction, which we'll learn the mechanism for in Module 16, you take your ketone and you react it with hydrazine in potassium hydroxide and heat it up, and you get the same effect. You're going to be removing the carbonyl so that you have the same carbon chain. Here is your carbonyl carbon minus the carbonyl. Now the cool thing about the Wolff-Kishner reduction is that the driving force is the release of nitrogen gas. And so this makes this a more favorable reaction. It also doesn't use any heavy metals, which makes it a more environmentally friendly reaction. And once the nitrogen gas leaves the reaction, it cannot go back into the reaction. So it has a pretty solid driving force. So the reagent H2NNH2 is called hydrazine, and you can also see it written out sometimes as N2H4. Both of those things are referencing hydrazine.